Right then, so today we are going to be looking at the damped unforced linear harmonic oscillator. Now, I know it's a big title, but essentially what we're going to be doing is we're going to be looking at this system here and we're going to try and find an equation for the displacement of this mass here in terms of time, the mass m, the, what do you call it? Damping constant and the spring constant. So, right, so let's start by looking at our system and saying what forces we've got. So we know that in our system, the sum of the forces is going to be equal to, so we're getting force from our spring constant here, from our spring even, so this is going to be minus kx, and we're also going to get a resistive force from this little damping thing that we got going on here. So that's going to be BV, where V is velocity and I should have said X is displacement. Anyway, we know that the sum of the forces in a system using Newton's second law is going to be mass times acceleration. So we can write that down there, lovely. And you can notice we've got acceleration, displacement and velocity all in one. So we can also use a little bit of calculus here, and we know that acceleration is equal to d2x over dt squared, and we know that velocity is equal to dx over dt. So we can get all the variables, well, not all of the variables, but we can change these variables into their derivatives of x. So what have we got? So we got m, then d2 x over dt squared equals minus kx minus b dx over dt. Right, lovely. And what I'm going to do now, it looks a bit messy at the moment, but we've got two negatives here, so I'm going to bring them over to the left-hand side. And I'm also going to divide through by m as well. So we're going to do two steps in one here, but it shouldn't be too hard to follow. So we're going to have add, and then I'm going to move this term just to keep it all nice and neat. So we got that there, b over m, then we have dx over dt. Then we're going to be adding k over m times by x, like that. Lovely. Right then, so what we've got going on here is going to be a second order differential equation. And fortunately, it's equal to 0, which is quite nice for us, which means it's homogeneous. So we can solve this relatively easily if we let. Right, so first of all, we got to clean some of this stuff up. So I'm going to let what is it? I'm going to have to consult my notes here because I've forgotten, which is a bit embarrassing, but it's fine. Okay, here we go. Right, so if we let b over m be equal to 2 gamma, and then we also know what k over m is equal to. We know that omega is going to be equal to root k over m, which means that omega squared is going to be equal to k over m. So we can substitute in those values here. So we can have d2x over dt squared, add, so we're going to have 2 gamma dx over dt. Then we're going to be adding that to omega squared x, and that's all going to be equal to 0. So now we can solve this. Now we've tidied it up a little bit. We can solve this equation. So we know that what should we do? Should we let, if we let p be equal to oh no, actually no, I've done that wrong. Let x be equal to e to the pt. So we're going to use this exponential term here because we know a fun little fact about exponentials is that if you derive differentiate. I always say derive. If you differentiate an exponential, you're going to get the constant term brought down, and it's going to stay as it is, which is quite a nice property to have when we want to solve this equation here. So we're going to let x be equal to e to the pt. And this means that we can say that d2x over dt squared is going to be equal to 2, is p squared, so it's p squared e to the pt, add, and then it's going to be, so we're going to bring down the 2 gamma, and then we've just got p e to the pt there like that, and then we're going to be adding that to omega squared e to the pt, that's going to be equal to 0. And we can divide this all by e to the pt, so we're just left with p squared add 2 gamma p add omega squared, like that. Lovely. And this is in the form of a quadratic, so we can use our good old quadratic equation to solve this one. So we've got p is going to be equal to, so it's minus b, so it's going to be minus 2 gamma. We're going to have plus minus root 4ac. A is just 1, so it's just going to be 4. Oh wait, what? Have I done that right? 4ac. Oh, my notes aren't adding up. Why my notes aren't adding up? Wait, I think I might have done this wrong. Anyway, I'm just going to continue because why not? 4ac, yeah, so if it's just 4 omega squared 0 minus, it's going to be minus b squared, so minus 2 omega, which is just going to be, oh no, 4 gamma, minus, blah, right. We're going to be minusing 2 gamma squared, so that's going to change into 4 gamma squared like that, and that is all going to be divided by 2a. So, and since a is 1, that's just 2, and that means that we can do a little bit of simplifying. This is why we set b over m equal to 2 gamma instead of just gamma, because it makes this simplification so much nicer to do. So if that's 2 there, that's 2 there, so we can divide through that quite nicely and just be left with gamma. And then we can also, if you take out a factor of 4 out of this root here, so if you group, take a factor of 4 out of this omega squared and the gamma squared, you're just going to be left with 4 brackets omega squared minus gamma squared. And then if we take the 4 out the root, when we root 4, we're going to get 2. So we're going to get a 2 outside this root, and conveniently we've got a 2 down here, so that is just going to disappear, those 2's, and we're just going to be left with this. I've done this wrong. Right then, well, this is a tad bit embarrassing because I've just consulted the good old notes as to why I've got this wrong, and it turns out I've got my good old quadratic formula wrong, which isn't ideal. So I'm gonna have to scribble this out. It's a bit messy, but you're just gonna have to live with it. So I was right with the 2 gamma plus minus root, and then it's b squared minus 4ac. Whoops, oh well. What are you going to do? So that's just going to be 4 gamma squared minus 4 omega squared 0 all over just 2. And then I'm just going to quickly do this last little step, and I'm going to actually show you what I mean here when I was waffling earlier, because I feel like if I take it a little bit slower, then I should be able to explain it a bit better and not mess up on things like the quadratic formula. So it's going to be minus that, plus minus, and then we're going to take this 4 out, and it's going to be rooted into a 2, so we're just going to be left with that 2, and it's going to be gamma squared minus 4 omega 0 over 2, and then boom, we got that. So that means our final solution, oh, that's gone off the page there. There we go, I'll just show you that. So when you take the 4 out of the root, it turns into 2, which is all quite lovely. So our final solution to P is going to be minus gamma plus minus root gamma squared minus omega squared. Lovely, 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 lovely. Right then, so we there's a few different right. So we've done a lot of maths now, but we're going to start looking at. We've got to a position now where we can start looking at what this actually means. So there's a few different cases which can occur, and this is all dictated by what happens under this square root. So the first one is when gamma squared is going to be greater than omega squared. So if we write this down, when gamma squared is greater than omega squared, over damping occurs. Right then, and this means that we're going to have two real values for P. So our two values for P are going to be P1, let's say that's equal to minus gamma, plus root gamma squared minus omega squared. Then we've got P2 is equal to minus gamma minus root gamma squared minus omega squared, like that. Lovely. Right, and when this is the case, that means that our general solution is going to be equal to, so we're going to have the displacement x in terms of time, so displacement as a function of time is going to be equal to a, e, and then it's going to be p1 up here, p1t, add b, e, then we've got p2t, where a and b lie in the set of real numbers, so they're just constants. Right, and we've got that equation from, because earlier we said, where did we say? Up here, we said x is equal to e to the pt, and since we have two values for p, that means that we're going to have two different values up here, and we're also going to have our constants in front of it, like that. So that is the case for overdamping. That's quite nice and straightforward, which I can't say the same for our next couple. Well, actually, this next one's quite nice. I'm just going to get a new sheet of paper here. And nice clean slate. Here we go. So the next case is when within the square root we have gamma squared is going to be equal to omega squared. And this is called critical damping. So yeah, critical damping occurs when gamma squared is equal to omega squared. Right, and if gamma squared is equal to omega squared, then our little p is equal to minus gamma plus minus root gamma squared minus omega squared. If these two things are equal and we're minusing them, then it's just going to be equal to minus gamma, which is quite nice for us. So that means we're going to end up with x as a function of time is going to be equal to a e to the, so it's going to be minus gamma p, and then we're also going to have add, so we're going to have that added to b t e to the minus gamma t. Oh, I've wrote a p there. That shouldn't be a p, that should be a t. There we go, that's lovely. You can see that we've got e to the minus gamma t in both these terms. So that means that our final equation for when gamma squared is equal to omega squared is going to be e minus gamma t. Then we're going to have a lovely set of square brackets around that. And then we're going to have add bt. Right, so those two are quite nice. I'm scrolling down my notes here because this next one confuses me a little bit. But we're going to have a go. So this next one is going to be when gamma squared is less than omega squared. And this is when under damping occurs. Right. And you can notice that in our equation, p equals gamma plus minus root gamma squared minus omega squared. If gamma squared is less than omega squared, that means this here is going to be a negative number. And that means we're going to have a square root, and we're going to have a negative number in that square root, which isn't very nice, as that would lead to complex solutions. So a little thing we got to do first is we got to define a new variable, omega, and we're going to say omega squared is going to be equal to gamma squared naught minus, oh no, that's omega squared. Omega squared minus gamma squared. Right, and then this means that omega is going to be equal to, or I should say plus minus actually, that's poor maths. There you go. Plus minus omega squared. This is big omega as well. We've got a little omega. I should probably have used a different variable, but oh well, it's too late now. That means it's going to be equal to this here, if we just take square roots of both sides. And this also means, right, so this, since this is both plus and minus, and there's no sign in front of here, what we can do is we can just, we can take out a factor of -1 out from under this bracket. I'm going to write over here actually. So we can say plus minus omega is going to be equal to root, and then if we take out a -1 out of this bracket here, out of that term, then we can say that that is going to be equal to gamma squared minus omega squared naught. And since we've got a -1 underneath this square root, we can then take it out the square root and turn it into the imaginary number I. So we've got this going here. So we've got that works quite nicely. Right, so this is quite interesting now. So all I'm going to do is I'm just going to I'm going to flip these two over. So imagine these two they are equal to each other, but imagine like they're just on two sides of the equation. Like forget this little middle bit is here. So I'm going to flip these over, and I'm going to end up with plus minus omega I is going to be equal to root gamma squared minus omega squared naught. There we go. What a lovely jubbly. So this means that our value for P, so our first value for P, because we get two solutions, is going to be equal to minus gamma plus I omega, like that. Our other value is going to be P2 is going to be equal to minus gamma minus I omega, like that. Lovely. So then this comes a little bit of a tricky part. So that means this will give us e to the P1 is going to be equal to e to the minus gamma add I omega, which we can see that since we've got these two being added in the indices, is that the right word? I'm not quite sure. Then we can have e to the minus omega, minus gamma even, and then e to the I omega here, and we can do pretty much the same thing for this. So then we can say that P2 is going to be equal to what we're doing, e to the minus gamma, e to the minus I omega, like that. And now we can see that we've got a complex number to the power of e, or no, e to the power of a complex number. And a little fun fact about complex numbers is Euler's identity. So e to the theta, or it should be, I've done that the wrong way around, e to the I theta, I prefer that, is going to be equal to cos theta add I sine theta. That's just Euler's identity. So we can also say that e to the I omega is going to be equal to cos omega add I sine omega, and then this also gives that e to minus I omega is going to be equal to so we're going to have minus omega inside the cos, but if you have a minus inside a cos, you can just change it into plus, which is quite convenient for us. So we can just say it's cos omega there, and then if you have a minus inside a sine, you can't just change it to a plus, but you can just move the minus outside. So we can say that it's minus I sine omega, like that. So that would give us that our final equation would be x t is going to be equal to a, and then we're going to have, so we're going to use P1 first, so it's going to be a, and then in this example here I haven't used t, but imagine that I've put a t in here, so then that'd be minus gamma t, and then e to the I omega t there, like that. So what was it, e to the minus gamma t, e to the I omega t, like that. And then we're going to be adding this to b e to the minus gamma t, e to the minus I omega t, like that. And we can see quite nicely that we can take out a factor of e to the minus gamma t. So we're just going to do that straight away, get rid of it. A e to the I gamma t plus b e to the minus I omega t. Oh, I said gamma there, didn't I? I meant omega. Right then, that means we can substitute in our identities. So that means this is going to be equal to, right then, so this is where it gets a bit difficult, which I'm not too happy about. A, and then, right then, I'm just going to have to do this maths. I don't know if I can talk through it, but I'll try. So we're going to use Euler's identity up here, similar to what we wrote here, only I didn't include the t there. So it's just going to be cos omega t add I sine omega t. Then for this one, we're going to be adding, oh, there should be an a there. That's all. I've sort of run out of room here. Well, imagine there's an a there. There's an a there as well. Trust me, it should be there. And then this is going to be b cos omega t, and then since we set up here, there's the minus is brought outside the sine function. We're going to have b I sine omega t, like that. Right then, so we've got two imaginary terms here, which I am not very happy with at all. But before we deal with them, I'm going to do a little bit of rearranging. So let's see what we can do with this one here. We've got, oh, I've put a bracket there, I shouldn't have. I'm all over the place today. So what have we got going on? We've got two cos omega t's, we've got two sine omega t's, so I feel like that's a pretty good place to start. So if I start off with doing, there's an a in front of that cos, and there's a b in front of that cos. So I'm going to say a add b, and then I'm going to times this by cos omega t, and then we've got an a I in front of this sine omega t, and we've got a minus bi in front of this sine omega t. So that means I'm going to be adding, if we have a I minus bi and sine omega t here in this form here. Right, this works out quite nicely, because we have to remember earlier we said that a add b was just a and b were just two numbers, just two constants, and so was an I is just a constant as well. So we've got no variables in these functions. The only variables that we've got here is t, omega, t, gamma, and that omega there. So what we're going to do with these is, I know when you have a cosine and a sine next to each other like this, you can do, I can't remember what it's called, but I know it's got a special name, this little identity, I suppose it is. Cos theta is going to be equal to, you can write this as r cos, and then it's going to be theta plus, I think it's delta, I mean, it doesn't really matter. You can when you have a cosine and sine next to each other, you can combine them together and write it as a cosine when you've got like theta, where you've got theta and delta here like this. And this is quite important, and this is quite handy, because this r is going to be equal to the square root of, in this instance here, I'm using a and b. So this a and b is separate to these a and b's, by the way. They're not the same thing. They're just arbitrary values I've just chosen. Not values, just constants I'm using. Anyway, so yeah, r is equal to a squared add b squared. And this squared is the very key bit, because if this is constant, and if this is a constant, bear in mind this constant is going to have the imaginary number I in it. We know that once you square I, you just get -1. So that turns it into a real number again. We can deal with the real numbers quite easily. And we also know that a add b is always going to be bigger than a minus b, I think. So we can say that this value is always going to be bigger than that value. So that means this value is always going to be bigger than that one. Or I think that's how it works out. Actually, that doesn't really make sense, but it makes sense for the purpose of this video. So if we are squaring this value here, that's going to give us a real number, which means that we're going to get a real number inside the square root, which means that which means we have a real number inside the square root, and it is going to be positive, which means that we can have r is going to be a real number as well. It's not going to be a what should we call it, complex number. So we can write this whole term inside here as just like a function of cosine, which means that our final function for this little oscillator thingy bobby is going to be equal to e to the minus gamma t. Then we're going to have big brackets here, and then I'm just going to use e instead of r because I think it's quite nice. I'm going to use capital E though. Capital E cos, and then our constant in this case was theta, but not our constant, our angle in this case was theta, but up here in our actual what do you call it, solution, I suppose, it's omega t. So we're going to have omega t, and then we're going to be adding, we're going to add delta here to that. And then this also means we've got a constant e here that we can take out. So that means our final equation is going to be e, it's going to be capital E, then e to the minus gamma t, and then inside these brackets we're going to have cosine omega t add gamma, add delta even. Right, yeah, that's pretty much it. We've got some nice stuff going on. That last little one is a bit dangerous when you deal with complex numbers, but I know I didn't really explain it all too well, but that's because I don't really get it all too well. And I know there was some famous mathematician which said, he said something like, anyone who claims to understand complex numbers is lying, because you can't really understand them. Well, I can't, certainly. So anyway, yeah, that's it. That's it for this video.